substitution. And essentially, when you see something like this in the problem, then you do a substitution. You let x be, if it's like that, you know, let x be a sine theta. If it's like this, you let x equal a tangent theta, and so on. Okay. And I left all these formulas up here because these get used quite a bit when we're doing these kind of integrals. Okay, so let's go to the first example. The integral from 2 to 5 of dx over x squared minus 1 to the 3/2. Okay, so here, this compares well with this last one right here. And, you know, a, if we let a be 1, so a is 1 here. So that means that the substitution is going to be x equals just plain old secant theta. Okay. There's a couple of ways you can go about this. You can leave the limits of integration from 2 to 5, but just remember that it's x equals 2 to x equals 5. Now, this leads to a couple of things. If x is secant theta, then we use this right here. So x squared minus 1 is going to be tangent squared theta. And simultaneously, it leads to, if you take the derivative of secant is secant theta tangent theta. The formula is on the first page, by the way, the derivative of secant. Okay, so this is going to get replaced with all of that. And this one and this one gets replaced with that. Okay, and you can leave limit integration like that. Sometimes it's good to change them, but usually not. I'll give some example. In this case, it's an example of not really useful to change it. So again, the dx becomes all this. And this becomes tangent squared theta, and that's all raised to the 3/2. Well, just remember these are x's, not thetas. Okay, so we have secant theta, tangent theta, d theta, and then down here we're going to have tangent cubed of theta, because the 2 and that 2 kind of reduce each other off. Okay, now there is a technique that I might have forgotten to tell you guys about last time when you have integrals like this. So this is like a trigonometric integral now. If you have secants and tangents, or if you have like a combination of things, you can always switch everything to sines and cosines, and that might help if you can't see another way to do it. Okay, so the derivative of tangent is secant squared. There's no secant squared that we can get out of here. The derivative of secant is secant tangent, and we can't just change all of these to secants. So, or I guess we could reduce one of these off, right? We could just reduce that to that. The derivative of tangent is secant squared. This is just a plain old secant, so you know that's not going to work using trying to make it some power of tangent. And then the derivative of secant is secant tangent, and so we don't have. That's going to be pretty tough. But sometimes it works to switch everything to cosines and sines. So like, for example, this is secant is 1 over the cosine. And the tangent is sine over cosine. Okay, and in this case, let's see what happens. So this cosine squared goes up top and reduces with that one, and we have cosine theta over sine squared theta. Okay, which you could also think of as sine theta to the -2 times cosine theta. Okay, now we can integrate that because the derivative of sine is cosine. So if we raise this by 1, so -2 plus 1 is -1. And now if you take the derivative here, you have a -1 coming down. So I'll put a negative there to counter that. So that negative will cancel it out. This reduces by 1 to -2. And then the derivative inside is cosine theta, which is right there. And that's going from x equals 2 to x equals 5. Okay, or we could write it as 1 over -1 over sine theta. But this is not, these are not in theta, so you can't just directly plug these in and subtract yet. Okay, so what you want to do is, at this point, let's go ahead and let's transfer everything, let's flip everything back. Now, this is kind of interesting how you do this. What you do, and this is usually a part of every one of these kind of problems. So there's first of all, there's the substitution part, then there's taking the integral, and then there's like coming back, giving it back into x's, because the original problem is in x's. So you want to get it back into x's. So what you do is, let me do this. I'll do the right here, and then we'll finish the problem off down here. Okay, so you draw a triangle, okay, with an angle theta, and then you say to yourself, okay, if x is equal to secant theta, well, that means that secant theta is x, right? Or x over 1. And the secant is the adjacent over the hypotenuse. Wait, it's the hypotenuse over the adjacent, I'm sorry. Hypotenuse over the adjacent, okay? That's the secant. So this is a right angle. So if that's 1 and that's x, and this is the square root of x squared minus 1, which is kind of what we got right here, see? Okay, that means that the sine is the square root of x squared minus 1 over x, okay? So we're going to plug that into here. And since this is 1 over a sine, then we just take the reciprocal here. Now you plug a 5 in. 5 in there is 25. 25 is going to be the square root of 24. And then subtracting and then a minus makes a plus. And plug a 2 in. 2 squared is 4 minus 1 is 3. Now if you factor a 4 out of here, it comes out as a 2. And that answer should work right there. Okay, any questions about that? So let's kind of look at an outline of what happened, okay? Number one, substitute. So our variable changed from integrating in x to integrating in theta. Number two, integrate. Okay, and that took us a while to do. That took us all the way to there. And then number three, substitute back. And and then evaluate. Okay, so you put it back into x's and then we evaluated. Okay, let's look at number two. Here we have another one. So again, you basically look and see what you have here. So this is the square root of 25 plus t squared. So a is going to be 5 in this case. And that gives us a squared plus t squared. And so we're going to use this middle one right here. So x is 5 tangent theta, because a is 5, because it comes from the 25 right here. 25 was right there, so that's 5 squared. So it's 5 tangent theta. Okay, and then this leads to two different things. 25 plus t squared. Oh wait, this is t, not x. Whoa. $25 plus t squared is going to be 25 plus 25 tangent squared. So 1 plus tangent squared is secant squared theta. So this is going to be 25 secant squared theta. And then dt. So you do that. So you look at this part right here, and then also you calculate dt. That's the derivative of tangent is secant squared, so that's 5 secant squared theta. Okay, then we go ahead and plug everything in. Now, if in this case our limits of integration are 0 and 5, so and then 5 is our a, and then 0 is a nice number, right? So that means when that happens, what you might want to do is just go ahead and change the limits of integration, and we could just do that. So let me do it both ways, though. Let me do it without changing the limits of integration, and then later with changing the limits of integration. But I think if you're integrating from 0 up to what your a, then that's going to be really nice. That's going to turn out pretty nicely. You're going to get nice angles that you can put in there. Okay, so dt will be 5. Oh, d theta. Okay, so this dt gets replaced with 5 secant squared theta d theta. And then down here we have the square root of 25 plus t squared is 25 secant squared theta. And that's from 0 to 5. That's from t going from 0 to 5. When you take the square root, you're going to get 5 secant theta down here, because you're taking square roots of everything. And then, so the 5s will reduce, and then this will reduce with that. So you have an integral from 0 to 5 of just secant theta d theta. Okay, let me go to the integral of secant theta is, I wrote a lot of these integrals right here. It's this one right here. The natural log of the absolute value of secant theta plus tangent theta. Okay. Okay, so now what you want to do is I'll do it right here, is go ahead and substitute back. We have our theta here. We know that t is 5 tangent theta. So if you solve this for tangent theta, you get t over 5. Okay, so if this is our theta and tangent is t over 5, then I can make that t and I can make that 5. And then this one right here becomes 25 plus t squared, which is this here. Okay, now the secant is going to be, the cosine is 5 over this. The secant is a reciprocal of that, so that will be the square root of 25 plus t squared over 5 plus, and then the tangent is 2 over 5. Okay, and now I can plug in the limits of integration. If I plug a 5 in, I'm going to get 25 plus 25, so I get square root of 50 over 5 plus 5 over 5, and then subtract and put a 0 in. If I put a 0 in, I'm going to get the square root of 25 over 5, that's 1, and then 0 plus 0. Now this is log 1, so that's going to be 0. And so I end up with the natural log of, let's see, square root of 50 is 5 root 2 plus 1. So this is going to be extra line there. This is going to be a natural log of root 2 plus 1. And I don't need absolute values because that's positive right there. So that would be the answer. Now, another way I could have done this, because this is really, these are nice numbers here, is this, like, so alternatively, this would have worked out nice here, I think, is it goes from t equals 0 to t equals 5. So t equals 5. So that means 5 equals 5 tangent theta. That means tangent theta is 1. That means theta would be pi over 4. Okay. And t equals 0. 0 equals 5 tangent theta, and that gives this theta equals 0. Okay, so instead of this right here, we would have going from 0 to pi over 4, and we would plug the pi over 4 into here, and we plug the 0 into here and here, and work it that way. That would be the way to do that. Now, you'll probably have to do some equivalent work to this, though. That's the problem. Well, well, you'd have to figure out what the secant of pi over 4 is, and also the tangent of pi over 4, right? Well, the secant of, well, that's okay. The secant of pi over 4 is root 2, and the tangent of pi over 4 is 1. So you're just going to get the same thing. Yeah. You get the same thing. That's root 2, that's 1. This is 1, and that's 0. So that goes away, and you just end up with that. Okay, sometimes you really have to do this alternate route. So you just have to keep in mind that that's an option that you can use. Okay, let's go to number 3. evaluate the integral from 0 to a of 5x squared times the square root of a squared minus x squared dx. Okay, this one is the top one. And here we have a's instead of like a specific number. So we'll see how that goes. So I'm going to make this substitution, which leads to a squared minus x squared, this part inside here, being a squared minus a squared sine squared theta, which is a squared cosine squared theta. Okay, that just comes from the identity 1 minus sine squared is cosine squared. Okay, and then dx will be a cosine theta d theta, taking the derivative here. Okay, so x squared, that's going to be this. So that's a squared sine squared theta. Okay, that's that. And then we have the square root of this. And then we have the dx part. And that's all that. Okay, so the dx part's all this. Okay, for this particular problem, I did find definitely, and I'm just gonna go, we're just gonna do the alternate route right off, because I found that's the easiest way, that's by far the easiest way to do this, okay? If you just do the alternate route, that is, instead of 0 to a, and then keeping these in x while we have this integral in theta, we switch everything to theta, okay? So we'll go ahead and do that right here. So x equals a. That means that a sine theta equals a. Sine theta is 1. That means you have theta is pi over 2. Okay, so that's going to be pi over 2. And then the lower limit, 0. You have a sine theta equals 0. That gives you sine theta equals 0. That means theta is 0. Okay, so you're going integrating from 0 to pi over 2. Okay. So let's see here. Let's try to collect everything together. We have a 5 here. We have an a squared. When you take the square root here, we'll have an a, and we'll have another a. So we're going to have a to the 4th and all. Here we have a sine squared. Here we're going to have a cosine, and here's another cosine. So we'll have a cosine squared theta. Okay, so we have sine squared, cosine squared theta. And so this goes back to like in the previous section, where what do you do when you have sines and cosines and they're both even? Well, you can use the identities to the square angled identities to reduce it down. So what we want to do is you want to look at there is, where is it? Oh, these two right here. These two right here. So these are the two that these are typically going to be the two that you're going to look to do. Just plug those in. In this particular case, I'm going to use this one first, okay? I'm going to use that one, and I'll show you why. So sine 2u is 2 sine u cosine u. It's because I have sine squared cosine squared. Okay, so basically,
Brother Hurst, I have a question real quick before you continue.
Yeah.
What happened to the square root a squared cosine squared theta?
This right here?
Yeah.
Okay, so one of them went to here. So that's a squared, and there's an a, so that's a cubed, and then another one more makes it a to the fourth.
Oh, okay.
And then the cosine went to here with this other cosine.
Okay. Thanks.
Okay, so what I did here is I put a 4 there. I just pulled a 4 out of this. No, not really. I put a 2 here, and I have a sine theta, cosine theta, and all that's squared. So the sine, when I square that, I'm going to get sine squared and cosine squared, but I'm also going to get 4. So I put a 4 there to counter that. Okay, and now I'm going to, I guess maybe I shouldn't have done it this way. Oh, I should have just done it the other way. Oh, well, that's okay. So here, I'm going to get sine 2 theta squared. Okay, now still we have the same kind of problem because it's squared. But what I'm going to do is I'm going to use this right here, this formula here. Sine squared is 1/2 of 1 minus cosine 2 theta. Okay. So this becomes 1/2 1 minus cosine 4 theta. Okay, so if I'm multiplying everything out, I have 5 a to the 4th over 8 minus 5 a to the 4th over 8 cosine of 4 theta d theta. Okay, now I integrate, and that gives me 5 a to the 4th over 8 theta minus 5 over, okay, so sine 4 theta is the key. So the derivative of sine 4 theta is cosine 4 theta times 4. So this will be, instead of dividing by 8, I'll have to divide by 32 now, because I'll have a 4 coming up. Okay, and this goes from 0 to pi over 2. Now, here's why I really needed to switch these limits of integration, use that option, because you have a 4 theta right there. So that's, if you have multiple angle, then that's going to be really hard to figure out how do you do it from there. It's the easiest thing is to switch it here, because now I can just plug in this pi over 2 here, and we're good. Okay, so I plug the pi over 2 in for theta. So pi over 2 here gives me theta, pi over 16 now, because I'm multiplying this 8 by a 2. Okay, and then when I plug the pi over 4 in, I get sine of, okay, so pi over 4 times 2 pi would be, times pi over 2. 4 times pi over 2 is going to give us 2 pi. Okay, and then subtract, plug zeros in. If I plug zeros in here and here, I'm just going to 0. So sine 0, 0, and then plugging that in is going to give me a 0. Also, this is going to be 0. Okay, so the answer is just going to be this part. Okay, so 5a to the 4th pi over 16. Okay, great. Any questions on that, or you want to go to the next exercise? Okay, let's go to the next one. And this is the last one, by the way. There's not a lot of exercises on this homework assignment, because as you can see, they take, it's quite a bit of work to do these. Okay, so here we have 25 plus x squared, so that looks like this one here. Okay, so we make this substitution, and a looks like 5. A is 5. So 5 tangent theta, and again, dx will be 5 secant squared theta d theta, and 25 plus x squared will be 25 plus 25 tangent squared theta, which is going to be 25 secant squared theta. Okay, so we'll go ahead and plug everything in. Here, this is an indefinite integral. There's no limits of integration, so that's nice, I guess. 25 secant squared theta over, and then x is 5 tangent theta, and then dx would be this. Okay, so if you evaluate that, that's 5 secant theta. Let's reduce those. Okay, so here, let's think about where this is going to go. If we combine these together, we'll have secant cubed. And that doesn't really help us that much with our integration, because if we're doing it in secants, then we need a secant tangent somewhere, but there's a tangent in the denominator. That doesn't help. And if we're doing it in tangents, then we need a secant squared, and then this is a secant cubed. So what I'm going to do is I'm going to go ahead and use, so another option would be to change everything into sines and cosines. And I tried that, and that doesn't work out very well. So yeah, that was kind of a disappointment. So what we're going to do is take this secant and change that into tangent squared plus 1. Okay. And then put the 5 in the front. So we have 5 secant theta. And then this is secant squared is 1 plus tangent squared. Okay, now what this does is it gives us 2 separate integrals, because we can, if we have an addition in the numerator, then we can split it up into 2 pieces. Okay, so all of this times 1 first. And then all this times tangent squared. Okay, tangent squared over tangent always used to be tangent. Like that. Okay, this one we can take the integral of. That's just secant, okay? Because the derivative of secant is secant tangent, right? So that's just going to be secant. This one right here, we'll switch this one to the sines and cosines and see what happens. So secant is 1 over cosine. And tangent is sine over cosine. The cosines reduce, and we have 5 Okay, we just have 5 over sine, which is the cosecant. And we know how to integrate cosecant. That's, just go to the front page here. I put it right here for your convenience. This right here. So the integral of cosecant is negative log of cosecant plus cotangent. So that one's going to be negative log of cosecant plus tangent. No, plus cotangent theta. And then this one, of course, is just secant theta. And then we have a plus a constant. So if it's an indefinite integral, you have to remember to add a constant on. Okay, now what you also need to do, at this point is switch it back into x's, because the original is in x's, so you can't have an answer in thetas. So draw a little rectangle. Always draw it in the first quadrant. So here's theta. And we know that x is equal to 5 tangent theta. That means tangent theta will be x over 5. Okay, so that's, make that x, make that 5. This becomes the square root of 25 plus x squared. And then from this triangle, you pick off the cosecant, the cotangent, and the secant. And that's your answer. Leave absolute value signs there. So cosecant would be, it's 1 over the sine. The sine is x over that, so it'd be that over x. Yeah, that's the cosecant. The cotangent would be, it's 1 over the tangent. So the tangent is x over 5, so the cotangent would be 5 over x. Like that. And then the secant, okay, the cosine is 5 over that, so the secant is this over 5. This over 5. So, but it'll just reduce with that 5, so it should be just this. And then have a constant on the end, plus a constant on the end.